After the time of J.J. Thomson and his discovery of the electron, comes another name, a really important name in understanding what an atom is made up of, and his name is Ernest Rutherford. Ernest Rutherford actually happened to be a student of J.J. Thomson, but Ernest Rutherford was actually at the time well known for his own work with radioactivity. He studied the absorption of radioactivity by thin sheets of metal and won the Nobel Prize actually for his discovery of alpha particles that were emitted by uranium metal and its compounds. What's interesting about alpha particles is that, as it turns out, these alpha particles are actually little pieces of the nucleus of an atom, the size of a uranium atom, breaking off and leaving the atom. And what Rutherford didn't know, that we now know, is that these alpha particles have a positive charge because they're made up of two protons, but they're also kind of fat little particles because they are made up of two neutrons as well. So these are actually fairly large particles that he discovers. And he discovers these particles and is able to work with these particles because of a device that he sets up. He found that if he coated a metal screen with zinc sulfide, that every time one of these particles would hit the screen, that it would emit a little flash of light. So Rutherford and his assistant Hans Geiger would actually sit in the dark for a long time until their eyes became very sensitive, and they would try to count the flashes of light on the zinc sulfide screen. I guess it's not terribly surprising that later on Geiger develops an electronic radioactivity counter called the Geiger counter, because I'm sure he got very tired of sitting in the dark and counting little flashes of light. But Rutherford, because of this work, begins to believe that there's a problem with the plum pudding model, that probably these atoms are not actually solid at all. And so he sets out to use an experiment that will allow him to better understand what the positive and negative charges in an atom are actually coming from. So he sets up this experiment. We call it now his gold foil experiment. So in the center of one of his zinc sulfide coated screens, he placed a piece of very, very thin gold foil. Now, gold is extremely malleable. It's able to be rolled out very, very thin, so thin that the foil is only 0.00004 centimeters thick, which means that it's only a few atoms in thickness. It's incredibly thin. And he directs a beam of his alpha particles at this thin gold foil. Now, he accomplishes that by putting a radioactive source inside of a metal box, a lead box, and putting a small hole in that box so that any alpha particles that come out are actually directed in a beam. So, what did he discover? Well, as he was doing this, he understood that the particles, these alpha particles he had discovered, had considerable mass and they moved quite rapidly. And so he anticipated that virtually all of the particles would be able to penetrate through the gold foil. And although they might be scattered slightly by the collisions with the atoms, he assumed that they would mostly pass somewhat straight through, kind of like if you shot a bullet at a bag of sand. It's able to pass through, but it does deflect slightly. And when they did this, that's exactly what they found. They found that most of these particles actually were only deflected on the order of about 1 degree, so a very, very small deflection. So they did this over and over again, and they noticed that that was the case. And they asked then another assistant who was working with them, Ernest Marsden, to set up the experiment and watch for longer periods of time and see if any of the particles at all would actually be scattered through a larger angle than that 1 degree. And Marsden must have been a very, very patient man, because eventually he found that a small fraction, about 1 in 20,000 particles, would be scattered at an angle greater than 90 degrees. It was a shock to all of them, because they had seen so many particles passing straight through and had assumed that's what they would all do. By seeing this, it ended up telling them there has to be something more going on here. And so we come to the conclusions of Ernest Rutherford's gold foil experiment. What were they able to figure out? And because of this, we get a new atomic theory. Okay? So since most of these alpha particles were able to pass straight through or be deflected only by about 1 degree, Rutherford concludes that atoms are actually mostly empty space, and that there must be a tiny, tiny center in that. And eventually he ends up calling that tiny center the nucleus. The alpha particles that were deflected at somewhat small angles could possibly be explained by the particle itself hitting into something in the center of the atom, like the nucleus. But it was more likely that they weren't running into something, but instead were being deflected by something. We know from Thomson's experiment, and actually from our own lives, that opposites tend to attract, but like charges tend to repel each other. And Rutherford knew this as well. So Rutherford said maybe what's inside of this tiny little center is actually repelling these alpha particles. Now, since these alpha particles are positive, the only likely explanation for a repulsion then is a like charge. So he decided that meant that this tiny little center must actually have a positive charge. And then those tiny little numbers of particles that bounce back, the 1 in 20,000 particles that bounces back that Marsden finds, can only be explained by something that is in this tiny little nucleus that is also densely packed and heavy enough to reflect back something that's as massive as an alpha particle. Now, that takes a little understanding. So if you think about it this way, if we're throwing large balls, like a baseball, for example, and that baseball were to collide with something that is smaller than the baseball that we throw. So maybe we throw the baseball and it hits into, a golf ball. We would not see the baseball bouncing straight back because the baseball is so massive in comparison to the golf ball. It would just push the golf ball out of the way. The baseball might slow down a little bit, but it wouldn't bounce back. Well, Rutherford understood the physics of that, and he said, the only way we can explain that something is bouncing back is that the particle must be hitting something that's at least as massive as it is. So if we threw a baseball and it hit another baseball, our baseball could bounce back. Even more likely, if we threw that baseball and it hit a bowling ball, the baseball would definitely bounce back. So Rutherford proposes then that whatever is in there, even though it is extremely tiny, it is extremely massive. So he suggests then that this nucleus of the atom has a positive charge, and that the mass of the whole atom essentially is concentrated in this tiny little area that is just a small fraction of the total volume of the atom itself. So Ernest Rutherford's atomic theory says that the atom is mostly empty space, but has a tiny, massive, positively charged center called the nucleus. So his atomic model might look something like this. He recognizes from J.J. Thomson's experiments that there are electrons, but he says those electrons, and he didn't really have a great explanation, but those electrons must be somewhere around this teeny tiny little nucleus that has a positive charge. Later on in his life, as Rutherford kind of reflected back on what this discovery meant, this finding that every once in a while a particle would bounce back, gave this quote, and it's kind of interesting. If you think about when this is happening in the early 1900s, something like 1911. It's just prior to World War I, so they've got a lot going on in the world. He's thinking of things in his world like tanks with shells and so on. And so he has this explanation for how surprised he was. He says, "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. It was just so shocking that anything ever bounced back that it made Rutherford realize there has to be so much more of an explanation about what atoms are like." But how small? How tiny would it have to be for only 1 in 20,000 alpha particles to bounce back? Well, it would be like this. If we took a marble, which is about 100,000 times smaller than the diameter of a stadium, and we put that marble on the 50-yard line, dead center on the middle of the football field, and we used that tiny little marble to represent the nucleus, the outside diameter of the stadium itself would represent the outer edges of where we find the electrons.